Good morning, everyone. My name is Shri Iyer. I'm the Associate Director of the TransCore Transportation Center, based here at NYU and for other partner universities. Our next section is on the USDOT connected vehicle pilot tests that are happening around the country and focusing specifically on the New York City DOT pilot, which I'm proud to be able to work on. So to talk more about that and to introduce our speakers, I'm going to ask Camille, Director of UTRC, to come up and take it away.
Good morning, and I would like to introduce my panelists, Jonathan Walker and Mohamad Talas and David.
Give me a microphone, please.
We all heard about the connected vehicle, maybe the pilot program in New York City, and it started 3 years ago. This panel is going to give us an update about the program. It's a national program. I have to bend in the mic for you. It's better? It's all the way out. So we have the Jonathan Wall, who is the project manager for a USDOT for the connected vehicle connected pilot program at the U.S. Department of Transportation. We have Mohamad Talas at the U.S. Department of Transportation. He's a project manager for the New York City connected vehicle program. And David Benevelli is the project manager for TransCore, who's actually doing the work for the program. So I guess we're going to give the podium first. Great, I can myself now. To Jonathan Walker, who has some presentation, who's going to give us the perspective, the national perspective on the connected vehicle program. Yeah.
First of all, thank you very much. My name is Jonathan Walker, State before I'm with the U.S. Department of Transportation. It's always an honor to actually speak in different engagements, specifically with the connected vehicle project. I'm used to pacing the room when I'm actually talking, so it's going to be a little more challenging for me to do a presentation standing behind a podium, but I'll give it my best. So I'm going to talk to you very briefly about the connected vehicle program overall. It's been going on for about 2.5 years. If you're not familiar with it, I'm going to provide you web links where you can actually get even more information because of the short time that I have. Trying to condense, a 2.5-year project into, 20 or 30 minutes is always very challenging. I'm going to let Mohamad, since I'm the program manager on the USDOT side in reference to New York City, I'm going to let Mohamad spend more time talking about the New York City DOT project. I'm going to focus a little more on Miami DOT and Tampa DOT, and then talk quite a bit on lessons learned. So to kind of give you an idea of what we are looking for at the USDOT, about 3-4 years ago, we decided we wanted to spur connected vehicle deployment, and basically using some level of wireless connectivity with vehicles, as well as mobile devices. And then not only that, we focused on measuring the deployment benefits, such as safety and mobility, as well as the effectiveness of this technology. And then last but not least, we wanted to resolve deployment issues, provide technical information, which I'll go more into details on where you can get this technical information, as well as institutional and financial information that various people who are interested in deploying technology. So if you're a professor, a research student, state DOT, local DOT, you've come to the right symposium, because I'm going to provide you free information and data that you can actually use to further your research or either go into actual deployment. So the connected vehicle deployment is broken up into 3 phases. The first one was awarded in September 2015, where we required the New York City DOT, who was awarded YDOT, Miami DOT, and THEA, that's the Tampa-Hillsbury Express Authority, we awarded them a contract to deploy connected vehicle technology. However, the first year, 12 months, we spent basically having them to document their concept, the system architecture, the data plan. I mean, it was very intensive. You talk to anyone who worked on those projects, we spent a whole year just documenting and trying to get an understanding of what's actually going to be deployed before we even provided them any type of funding. Then phase two, once they submitted, I think it was well over 12 or 14 different documents, we went into phase two, which is the design phase, to build and to test. Actively right now, YDOT is actually, all of the CV deployments are in this phase right now, but YDOT is actually physically deploying and building, as well as THEA and New York is well on its way. The last phase, once again, is where they actually maintain the deployment. We require them, even after the contract is ended, to continue to operate these deployments as well. So YDOT's main purpose was to reduce the number of reduce the number of casualties due to severe weather, and you'll see this a little later on along the I-80 corridor. Likewise, Tampa was having major congestion issues and trying to improve safety in the morning time with their expressway. And then New York City, once again, is probably one of the, it will be the largest deployment of connected vehicle technology. So YDOT. So YDOT, whether you believe it or not, they have one of the largest level of fleets going through I-80 than any other state in the United States. They have severe weather conditions, which many of you may be familiar with, and an adverse, this adverse weather in turn also caused a lot of deaths due to a high rate of crashes. So here's an example, and you may have seen this on television, but I can tell you right now, when YDOT came to do their presentation, they actually ran like a 5-minute video while they were talking. And it was actually one of these crashes where it got caught on camera. And while the gentleman was talking, you could actually see crashes occurring. And you get to a point to where it actually made you cringe because you knew the next car was coming. And then after about 3 or 4 minutes, it stopped. And then another minute later, you see another truck coming in there. These are some of the numbers that they actually have. As of 2017, there were 408 crashes, and they had a number of fatalities as well. When we started phase two, when we started having a conference call with them, they would report how many crashes they've had and also how many deaths. So this project in YDOT is very crucial to helping to deploy connected vehicle in areas where the weather is very adverse. Proposed solution. So YDOT actually is deploying 75 RSUs, roadside units, along the I-80 corridor, well over 400 vehicles with DSRC technology. They have various B2B applications, such as forward collision warning, disaster distress notification, as well as B2I applications, such as situational awareness, spot weather, and work zone. As far as the additional pilot elements here, they are using a SCMS, which is a Security Credentials Management System, which basically ensures that information is trusted when it's communicating between vehicle to vehicle or vehicle to infrastructure applications. So they also, here's a breakdown of phase one and phase two and how they're moving forward with phase three. They're actually almost in phase three and ready to do a demonstration project in a few more weeks, actually. THEA. So Thea, once again, had major congestion. So they actually have a freeway that they use in the morning time that basically allows the bulk of the traffic to come into the Tampa area. And then they reverse lanes coming back. And occasionally people actually get confused and they actually go in the wrong direction. So you have hundreds of cars going in one direction, someone turns in and going in the opposite direction. You can obviously see there's major issues with traffic flow there. They were also trying to optimize the bus transit priority, traffic flow optimization. Rush hour collisions were big issues because people would get stuck on the Tampa Hillsborough thoroughfare, and they would actually get off and actually dump into the street, and that would end up causing more congestion as well. And they also have a light rail system which constantly experience a lot of accidents as well with vehicles. This is one of the areas where you see the bulk of the traffic actually coming in, but occasionally you would get individuals, like I said, would make a wrong turn and actually come into the expressway. They also had a major issue, believe it or not, on Monday and Tuesday mornings. They are near a courthouse. This intersection is near a courthouse, and the majority of people who were serving for jury duty would cross this intersection. Well, this intersection was one of the busiest intersections in Tampa, and you would get a lot of conflict between pedestrians and vehicles, and a lot of people would actually get hit in trying to serve jury duty by coming across the street, unfortunately. Once again, they were trying to optimize their bus route because of a number of the traffic conflicts that we're having. Here's the actual trolley car. You can see this Mercedes-Benz cutting in front of the trolley car, which is really not too smart, but and then once again, congestion. You guys here at New York City are always well aware of congestion that we have here. So some of the solutions that they had, so they did something very interesting. They actually looked at a number of the use cases that they had. All the connected vehicle programs had to come up with use cases and actually detail it out and then actually provide solutions. And here's just an example of how they actually mapped out the use cases versus the connected vehicle application. Now the USDOT had did a report several years before that, and they had basically published 60 different connected vehicle applications that are potential connected vehicle V2V and V2I and safety applications that were possible. But we did not map it like a lot of the connected vehicle awardees did. And this is one example where they actually look at morning backup, and they connected it to different applications that you see here, as well as pedestrian safety. They are deploying well over 1,600 privately owned vehicles, and I'll talk a little more about the lessons learned in that. 9 streetcar trolleys, and 10 buses, and 40 RSUs. One of the other things that's very big with all the connected vehicle projects, and I talked about earlier, is performance measures. How do you know that what you're deploying is beneficial? So we require all the CV pilot sites to do a very thorough analysis, and we have also independent evaluators that will actually assess the performance before and after the deployments. Lessons learned. So I'm going to spend a little more time on this slide and the next slide. So one of the lessons learned is assessing the infrastructure and the organization capabilities. As many of you know, there's a separate group who actually writes the proposal, implements the proposal, and then there's a separate group that approves it. So a lot of times you have to make sure that you're on the same footing, and that's what the organization capabilities are. So a lot of times what happens is a certain group or program will be awarded a contract, but they will have a challenging time getting things approved as it relates to, replacing legacy systems, receiving additional fundings to move forward with the contract. So it's very important that you do a very detailed assessment on your legacy system and take that in consideration. Otherwise, you're going to have a very costly deployment and possibly a lot of change orders. Institutional arrangements provide adequate attention towards the various driver applications as well. Data management. So with the connected vehicle projects, if you can just imagine, if you're sampling data at 1 to 10 times a second, then you multiply that times 24 hours, then you multiply that times 365 days, then you multiply that times 3 to 5 years, there's going to be a lot of data there available. And we're actually seeing that now with Tampa, who's actually, and YDOT, who's actually providing their data at this moment. Security is always a crucial issue, not only in reference to the infrastructure, but also the vehicles. We spend a lot of time looking at security as it relates to making sure that a driver who's using the connected vehicle technology, their identification and their locations and things of that nature are not made public from a security standpoint. System architecture, standards are very, very important. Even though we have 3 separate sites deploying, we were very successful in doing what's called an interoperability test to actually show that each one of the devices at each given site is interoperability with another. So theoretically, what you could do is you could take a vehicle from New York City and drive it to Miami, or either drive it to YDOT and would still operate correctly. Installation is very important, making sure that you hire the correct individuals, and then testing. Testing is very important, as you may be aware of, but making sure that you have the correct test equipment is essential as well at the given locations. And I'm going to spend the last few minutes on this website. I think a lot of times when we do presentations, we don't talk about the USDOT website. So this website right here, itsdot.gov/pilots. If you're a research student, you're a professor, state DOT, local DOT, this is the website that you want to go to. Why? Because literally 2.5 years worth of work is all on this website for free. All of the design documents that all of the CV Pilot sites have published, the USDOT has actually published them. They've submitted as deliverables, and we provided that. There's well over 50 different documents. So if you're looking at deploying, either you do one or two things. You either hire a consultant to read these documents for you, or either get a research student, but overall, it will tell you what you actually need to deploy connected vehicle technology. The phase 1, all the phase 1 documents, as well as phase 2. So even though we had phase 1, we had all the CV pilots to submit their documents, we had them to go back in phase 2 after they start deploying and revise the documents based on reality and what they're actually experiencing. And as well as we have a lot of lessons learned, little small tidbits that make a difference in actually deploying. For example, one of the problems that Thea had is how do you get people to participate in a connected vehicle project? How do you encourage individuals to use their own vehicles to come in at their own time and actually have someone else to deploy? So one of the things that they did is they offered a discount for those who had used the expressway. And in turn, those individuals would come in and they had it laid out to whereby the individuals spent no more than an hour during the installation phase. So they had gotten things to whereby it was very short and it didn't produce much inconvenience for the individuals. New York City, I'll have Mohamad to talk a little more about that, but they did some very interesting things to get participants. And then YDOT was sort of the same thing. They mostly recruited truck companies as well. So this website also has a number of videos that you can actually see interoperability tests being deployed, as well as each one of the CV pilot sites have their own website that we required them to deploy as well. So once again, spend some time if you get a chance to go to this website, and I'm quite sure that you will find it worthwhile. And here are the point of contacts. Kate Hartman, who's the program manager for YDOT, myself, New York City, Govind over Thea, and then I had mentioned about our evaluation, independent evaluation. Walt Durham is over that as well. And here are the individual websites for each one of the CV pilot sites.
Thanks, Jonathan.
Thank you to Jonathan to give us this update on the tour of the site. Now we're going to hear more detail about the New York City site with Mohamad Talas, who's going to give us an overview and an update about the New York City Connected Vehicle Program.
Good morning, everyone. First of all, I would like to thank NYU and UTRC for hosting and allowing us to gather together and exchange our experience and update our stakeholders and the public about the New York City Connected Vehicle Pilot, as well as other work around the country. So basically, my presentation today, I'm going to go over the project in general, fast. I'm going to talk about the status of the project today as we are in the making, and identify some of the challenges that we have experienced. As a project goal from the beginning, we keep our mission over here in DOT mission of improving safety. So we chose to participate 2 years ago in this project, basically to provide additional ability to drivers to drive safely, to the public, to the motorists. And we believe the connected vehicle technology can, as well as USDOT, as other researchers, can provide and improve safety in general and reduce accidents all around. And that coincides with our Vision Zero in New York City, which is improving safety, reducing speed in general. The project area was chosen to be Manhattan. We chose Southern Avenue, basically 1st, 2nd Avenue, 5th and 6th Avenue. And the cross street, we extended the cross street. We make some modification to major facilities like the Midtown Tunnel and the Lincoln Tunnel, the Triborough Bridge. And this is bounded by the FDR Drive for some highway applications. Also, we have chosen an arterial in Brooklyn near Flatbush Avenue from Grand Army to Tillery and some adjacent to cover the bridges. Our plan also to cover all the East River bridges from Queensboro Bridge to Brooklyn Bridge end to end. This illustrates basically our central traffic control system at TMC. Our controller that is a computer-based ATC controllers and the wireless modem that we use. As far as the V2I application, this will occur in all the pilot area locations. Wherever we have infrastructure is deployed with roadside units. V2V, obviously, it can work anywhere in the city where those two connected vehicles, they're going to meet and interact with each other. The overall goal of the project is to reach an 8,000 vehicle deployment. We focus from the beginning on the fleets. Our goal today is to deploy 3,000 taxis, 700 MTA buses, about 3,000 sanitation, DOT, and city fleet vehicles. And we are testing 100 mobile device to support impaired pedestrian application and help impaired pedestrian navigate their way at intersections. Obviously, the selection over here of our stakeholders and users and participants is based on basically the roadway classification as far as user that shows here in our illustration. So the taxi are very visible in Midtown Manhattan, and our fleets also, and sanitation whatsoever. The several safety application we have designed and demonstrated so far: vehicle turning right in front of a bus, forward collision warning, emergency electronic brake lights, blind side warning, lane change warning, assist intersection, movement assist, red light violation warning, speed compliance, curve speed warning, work zone warning and advisory speed for work zones, oversized vehicle for highway application as well as the curve warning, and emergency communication and evacuation application. The pedestrian, we have two different applications. One using the mobile phone, which is advising the impaired pedestrian to navigate his way as he crosses the intersection, and give him warning as he starts with the work indication in certain tones, and when the flashing don't work, the tones can change. We also have fixed device installation to detect pedestrian in crosswalk and send that message warning to vehicle. And that's by using video detection technology at several locations. Other application was more of a system management and maintenance application to support the project, which is our monitoring, OTA, over-the-air firmware updates, since we have a very large scale deployment, parameter upload and download, traffic data collection, event history, and others. The diagram here illustrates basically our vehicle participant stakeholders, the taxis, the buses, the sanitation, trucks, DOT fleets, and the pedestrian application. Our project is based on using DSRC, the 5.9 gigahertz, for all the onboard units and the roadside units. And that shows, this wireless communication shows over here. And from the roadside unit is connected to our traffic controller by Cat5, direct connections from the mast arm, and sending this information, the data that has been collected, over our citywide wireless system back to the traffic management center. And the traffic management center, over here, we have all the security measures to ensure the network security at TMC, and we are exchanging the data with the third-party TTI for performance evaluation. Texas Institute of Technology, which is an independent party and hired directly by USDOT to evaluate the three sites. Where we are today. Jonathan spoke about finishing phase one. Phase one basically was the concept of operation, the design, and the system management plans development. So we have developed the security management operating concept, plan, safety management plan, performance measurement, application deployment plan, human use approval summary, and training application plan, partnership status summary, outreach plan, and comprehensive deployment plan. And we are, since about 6 months, we are in phase two. Phase two entails detailed design, procurement, and installation and deployment. Phase three is the evaluation period. So far, to have a head start of our phase two deployment, we purchased pre-prototype almost 100 units from vendors to test the technology as we go on our procurement process, so they both can overlap and minimize any delays that can result from our process anyway. We have planned basically to use the city governmental process to procure the roadside units, onboard units, the ASDs, and all the other supporting units. So that is generally is a lengthy process, and we have completed basically a very much of a detailed design and have bid some of those contracts already, on most of them actually. The RSU, the roadside unit, was bid was completed, and we already have delivery now. We have so far over 15 intersections equipped with the roadside units. We are purchasing about 400 roadside units to cover all the intersections in the pilot area. And this number may exceed, may also increase as we go on in the deployment and identifying challenges. Roadside units, we have now over or close to 100 prototype, pre-prototype, let's call it, ASD units deployed in our fleet, DOT fleets, sanitation, MPA, and taxis. And again, was a head start for us to learn how we're going to install, how we're going to have the best installation template, their vehicle type, their onboard unit, interface cables, interfacing with the campus, and installing also the proper antenna for each vehicle. So right now we are in the making, and we have we have ongoing testing of the safety applications that we designed already. The softwares for most of those safety applications has been developed and tested twice by vendors, and we continue refining that as we go on. And we participated in interoperability test, as Mr. Walker mentioned. This is a sample actually of our roadside unit installation. And as we go on, we are continuing developing map message that is basically a digital map for the intersection, describing the approaches and the number of lanes and whatsoever. Planning the RSU installation, this has been completed. Developing vehicle installation kit design, this has been completed, and we are also working with basically 2 installation contractors for the ASD to handle most of our 8,000 onboard unit installation. This illustrates basically some of DOT installation here, the several antenna and some of the challenges and the location of the antenna on the roof and where the speaker has to be in. Our application basically is based on audio alert. 2 things is very important. We are not providing a text alert or screen alert to the driver. We are providing a tone or wording alert to the driver. So a speaker is needed for this installation, basically, and also you can, in some other installation you can use the existing vehicle speaker. The other thing is protecting privacy. Our approach is anonymous, and all the driver personal information is expunged and completely and not shared. Our strategy was to have at least 2 vendors here to provide the onboard unit. Again, to have to ensure compatibility, competitiveness, cost effectiveness, and interoperability too, as well, and reliable completion of the contracts, as if we have problem with one vendor over another. And so far, we are very much close to start the contracts with at least 1 vendor here with a major production. As I mentioned, we already purchased over 100 units and tested them, but officially it's going to go by the end of this month to have a registered contract to supply the 7,000 units that we have. Different antenna was basically analyzed and inspected for the cellular installation that we have. We have antenna that require to be mounted in drilling the roof of the vehicle with hard wire and direct connection to the ASD, the onboard unit. And we have some stakeholders, they would like to have that done to their vehicles. So one of the vendors proposed a glass mounting antenna. Okay, that's completely non-intrusive to the body of the vehicle, and it basically sandwiched to the windshield of the vehicle. However, the antenna is a little bit, this is the early version. We hope that we can reduce the length of that antenna as we go on. This is a sample of our fleet installation. Trucks and every vehicle types, there's a couple of challenges that we have to keep in mind. Where the antenna is being installed, the device where it's going to be installed, and if we have the right configuration also to interface with the CAV, with OBD2, the CAN bus of the vehicle. Every vehicle, make, model, and year has certain configuration for the bus. So we have to have that configuration in order to extract the data, the speed, the angle of the steering angle of the vehicles, or if there's left and right turn indicator on, and the trajectory of the XY as the vehicle is moving. The buses also, they chose over here, MTA chooses to have an antenna to be mounted on the front. And we have tested a few buses already with that, and we made some improvement on having a stronger adhesive also to have that antenna still. Taxi installation was going very fine. We have about a dozen of taxi already installed with a prototype. The only challenge over here, as you can see, the advertising board that sometimes is used on the roof of the vehicle. So the position of the antenna is very critical where you install it, because the exact XY coordinate, of that antenna on the roof, the exact by inches, is very important for the onboard unit algorithm. And it affects, if you move the antenna, it really affects the XY coordinate and the calculation, the trajectory. Sanitation, one of the challenges basically is that the sanitation vehicles are washed on a daily basis, so devices has to be waterproof. but we have already a couple of vehicle equipped with the ASDs. Cybersecurity issues, Mr. Walker spoke about it. Basically, the general theme here and the work on the national and the local level with us here, working together, the basic element depended on the trusted environment, protecting the vehicle and the infrastructure, hand in hand. So then that was to have a message authentication of the BSN, the SPAT message, the MAP message, and the TEM, and using the CMS, the Security Certification Management System, to ensure that data encryption to preserve privacy, and require a corporate certification using the standards by the IEEE and the SAE, organizational and IT security, and that's for the TMC. Basically, protect all the connections and the data exchanges, and the CV hardware also as well. The CV hardware, the OBD, will have a hardware security model as well as the TMC. Hardware security model protect basically the certificate key of that device. If somebody tamper with that device, the certificate will be erased. This identifies all the possible links that has to be protected by our security management system and our approach. One of the challenging issues is the data. Right now we are dealing with the size of vehicle. If this to be expanded, on its own now, it's a very large scale, and there is a tremendous amount of data that is being collected. So how do we manage that? How do we select the right data to conduct the performance measure analysis? Or it's the needed data, let's say. But as we grow on with expansion in the future of this technology, this is going to be an issue and need to be addressed. So we have developed certain scheme to basically to identify the data that we need and not to record all single data. So if you have an event or you have a message, we are only detecting 10 to 20 seconds before the event and 10 to 20 seconds after the event. So this is not open channel. Otherwise, you need, a very high band at each RSU location to transmit back all of those data. And we have used basically unicast wherever it's needed to monitor broadcast of any messaging or whatsoever. As far as the communication between the TMC and the RSU, we have, as we mentioned, we have hardware security model. We have another layer, DTLS, on top of for every device on the RSU, on the onboard unit, and at the TMC. And this is an added layer of end-to-end to ensure encryption of the participant data. And we also did some more edge computing on the RSU to minimize the transmission of all data back to the TMC. I'd like to focus, since we're short time, on the location accuracy. Our work was based on location accuracy using the GPS system. However, in Manhattan, we have the urban canyon. The standards calls for 1.5 meter error for connected vehicle to work effectively. 1.5 meter plus and minus, less than 1.5 meters. In the urban canyon environment, we have not achieved that using the GPS. However, one of our vendors demonstrated basically a roadside unit triangulation, which is using triangulation methods that are used basically similar to the satellite communication navigation system to improve that accuracy, and we were successful in demonstrating that and stopping the error and having basically sub-meter error. This is how basically this works. There is a communication between the onboard units and the roadside units, and you have the multipass error because of the reflections of the buildings, and you have a V2X locating engine on the onboard units that takes basically the flight time and the information from the RSU, the reference XY coordinate from the roadside units, and takes also the GPS information and identify accurately the vehicle location. This is basically a summary of this mechanism, which is the roadside unit triangulation. Vehicle sensors providing speed, providing trajectory, and roadside unit reference and flight time measurement, and that's what is the triangulation, and the GPS also. All those three data are analyzed by the fusion sensor here and identify the vehicle location. This is being tried for the first time, probably in the world also. This is a real-time demonstration, that we have done, and we verified the accuracy of the roadside unit triangulation methods. As we did that on the last basically 8 months, we have updated our specification to ensure we have that features basically in the roadside unit as well as the onboard unit. And the result here shows that we can have up to 80 centimeters, which is less than what our half of our procurement standard calls for. Other challenges basically was to adjust to the lower speed that we have in New York City, which is 25 miles per hour. Most of the connected vehicle applications that has been developed was based on high speed, anticipating that the vehicle have an accident with high speed. But when we have lower speed over here, we have different challenges we have to fine tune. The CAV bus interface, I mentioned that basically there is a challenge with vehicle types, with multiple vehicle types and make and models, so we needed to have a gateway device to do that. One of the vendors depend on that approach. And the many different vehicle and models that we are trying to use. With that, I conclude my presentation. Thank you very much.
We're going to hold the question for the end, and the panel is going to come. The next one is David Benevelli. He's representing TransCore. He's a lead contractor on the connected vehicles from NYC. And he's going to provide more additional information on the USDOT connected vehicle order.
I think I'm naturally a little closer to the microphone. Does that work? Can I see a show of hands how many students we have here today? I'm glad we have some. This is your future in transportation. It's at its infancy. Mohamad asked me today to talk about the projects use of standards. And we are strong proponents of taking standards, using them, and creating open systems so that we can interconnect and work with others. So I'm going to talk about a standards background, talk a little bit about the maturity of the standards, and some other comments on vehicle integration, which you've heard from Mohamad and Jonathan Walker about, and then spend some time on data collection and security. Our motivation is to help be on the leading edge. While we're not the developer of the standards, we're one of the first applicators of those standards. And that's put us in a tremendous learning curve. So this is a big overview of the context of the standards. You can see individual devices with the vehicles talking to each other, but they also talk to vulnerable road users and to roadside equipment, because that's where we connect into the infrastructure. And that infrastructure consists of traffic management centers, other field devices, and then subsystems that help provide the backhaul and management facilities that we need for our systems. Now, what you see on this chart are the linkages between those systems and entities or devices. There's a lot of glue behind that. There's the GPS system, which is providing the time reference, and the location reference. It's the base foundation for everything that's done. But the other piece of glue is the security system, because we need to work in a environment where we trust one another. So that is a pervasive subsystem throughout. There's actually 4 families of standards represented in this drawing. There's IEEE standards, which talk about the underlying 802.11p physical and media access layers of DSRC. There are SAE standards that work at the messaging and performance layers. For messaging, we have the J2735 data dictionary. We also have the performance standards, the first ones being J2945/1. But there are other standards dealing with the field devices. We've opened up the communications for those with NTCIP requirements and specifications and standards. We have 1202 for the advanced signal controller, and we also have 1218, which is under development as we speak, for the management of the RSU and its connections back to other devices and the traffic management center. You need to understand this is an overview of standards. There are a couple of things, especially the students here, that should be aware of. When you start dealing with standards, they reference other standards. So this is the top level view. You'll find many other layers to be involved in here, especially when you start talking about the security levels. But there are also nuances in the standards. As Mohamad and Jonathan mentioned, with J2945/1, the 1.5 meter accuracy requirements for vehicle locations, those are defined under open sky. And if you look at Appendix A.7 of J2945, it gives you a definition for open sky. If I were the DSRC antenna, it says, there's nothing between me and the horizon for 5 degrees. So I took this picture out on a lake of a wonderful view of open sky where you can probably see more than the anticipated 7 satellites. But this is our urban challenge in New York. This is looking up at 5th Avenue and 55th Street. We're a long way from having a site that meets the definition of open sky here. I was talking with one of the other speakers earlier, and we were talking about places that are actually worse than this, especially down along the side streets in the Garment District of Manhattan. So the standards, and there are a lot of nuances in implementing them. So now I want to spend a few minutes talking about our experience in applying the standards and what we've learned from some of those activities and fed back into the standards making process. As I mentioned, we are definitely learners in this environment. We're on the bleeding edge. There are no guides on how to use these standards. That's why Jonathan emphasized the existing documentation that we're putting together. A lot of that's driven by applying the system engineering process, where we start off with our CONOPS, looking at what we want to accomplish, and then going into the requirements to accomplish that, and then the designs that apply those requirements so that we can fulfill them. So the 3 CV pilot sites have had to work together very much hand in hand throughout this process. We'll get into a little bit more detail on that, but one of the things we were able to depend on were the certification programs that USD has helped put in place. OmniAir certifies the devices for DSRC operation, and that's a very rigorous test. They've actually gone through the first series of those. We're about 7 or 8 months into that, and we have one RSU that's recently been certified and one aftermarket safety device with a few more about to come online. But that's only an initial test. That doesn't mean it meets every condition. It meets those that are requirements of the standards. So we're going to focus on 4 different areas. I have slides for a couple of these. What I want to spend a little bit of time on are the PSIDs, the Provider Service Identifiers. Because previously, through much of the research, the MAP and SPAD have used the same PSID. The pilots, especially Tampa and New York, are breaking that mold because the data comes from different sources. The maps are actually generated by transportation agencies or operating agencies. So we're signing those at the source of the map data so that we can authenticate it from its inception to delivery. The life cycles are also different. SPAD information is good for seconds because it's telling you when the next signal change is going to occur. Maps have a far longer lifespan. But we're also using that lifespan and applying it to our security model so that we can make sure our devices remain online. So we have different security profiles. And the pilots are implementing this new strategy, and we're going to have more bleeding here on the leading edge. But hopefully that will make it easier as implementers move ahead with these systems. This is actually one of the screenshots of the culmination of a lot of the system engineering process work. We actually went through the requirements for the basic safety message, the BSM. And it's outlined with mandatory components in J2945/1 and in the data dictionary. But we, as actual projects, needed to go further. So we had to look at our requirements. 2945/1 allows you to omit vehicle type information for light duty vehicles. That covers vehicles under, I believe it's 10,000 pounds. So your light duty pickup trucks, your taxis, what people would buy individually. However, when you talk about fleets, you have a different set of requirements because we know there are taxi fleets built on light-duty vehicles. So we get into the integration issues and meeting our project needs. So we went through a very detailed process. There's about 200 different data elements and data frames defined in that J2945 standard. And we went through every single one of them to decide what was mandatory for our project, what was optional, and what we didn't care about. We also started doing our maps for intersections, and this is Flatbush Avenue and Atlantic Avenue, right by the Barclays Center. Understanding the standards, we have a generic lane model that defines the center line of the lane and a default width for those lanes. We use that no matter whether it's a pedestrian sidewalk, a vehicular travel lane, or a crosswalk. One of the things we discovered is in the standard you have that default width and then there's an incremental width that can be applied to it. Well, that incremental width wasn't large enough to support our going from the default 10-foot wide lanes in New York City to cover a 30-foot wide short crosswalk on its short side and 65 feet wide on its wide side, on that east side. So those are some of the issues that we're bringing back to the Standards Committee to try to address. We're talking about trying to do that by providing different default lane widths based on the type of lane you are modeling. This, if you haven't seen it before, is a photo we were able to get out of the USDOT archive, but it shows, if I recall correctly, this is 7th Avenue, and there's a lot of density here in traffic signals. On the avenues, they're about 250 feet apart. Well, with a DSRC range of 300 meters, we're expecting a vehicle may hear anywhere in the vicinity of 8 to 10 different maps at any one time that it'll have to sort through. So we've actually added specifications to reduce the power output level of the RSUs to try to manage this. We're just getting into initially deploying these RSUs, so this is an area that we're going to have to be performing some tests on and configuring the system operations. But we don't have, while we have recommendations in 2945/0, we don't have standards for what you have to do. That's giving us the flexibility to work in these areas right now. But there are some areas that we're going to have to talk about adding standards to. I want to mention the applications. As we talked about the interoperability test, there were actually 6 vendors there. The basic operation was the same, but the parameters to configure those basic applications varied by vendor. They may have fallen into similar categories. That doesn't mean everyone had tuned them the same. While we were actually working with vendors, we found that they took different approaches. One where your grandmother would be very comfortable braking, and others where everybody in the car but the driver was reaching for that virtual brake because they were scared at that point. So to work with the applications, we actually probably need some standards going ahead. And putting those devices in existing vehicles, as Mohamad mentioned, is proving to be a challenge. Because right now, while we can connect to the vehicle through the OBD2 port, the one piece of universal data we need, speed, to enable dead reckoning, is available, but none of the other data parameters we need for directionality of the vehicle, braking status are available. So we want to be able to make sure that the existing vehicle fleets can be updated so that they can participate in this infrastructure as it grows. Scalability and deployment. Well, you've heard we are talking about a large number of vehicles. To deploy that, we're looking at time frames being on the order of 23 weeks, and we're trying to overlap that with our tuning and operations, so we need a reliable mechanism to actually update the firmware and parameter settings in those vehicles. So we've been taking a lot of time to look at our over-the-air exchanges of data, using the standards and using the applications. We've taken a approach to network encoding that our RSUs can broadcast a download, and multiple vehicles can be listening simultaneously to update their software and firmware. We can also deal with the uploading of data logs from those vehicles. But data recording is a big issue for us because you heard Mr. Walker mention Thea's learning about the backhaul needs. We went in starting off realizing there's a tremendous amount of data that can be generated here. We wanted to make sure that all of it that we brought back had value. We didn't want to expend backhaul resources where we didn't need to. So we had to assess that data and look at our backhaul constraints. We also had to make sure we collected it so that we preserve privacy, because I'm sure that for all of you and our fleets, if you felt your privacy was going to be impinged, you weren't going to participate. So for an example, we looked at travel time and we looked at what it would take and how many messages a vehicle would generate going down one of the short blocks. We might see 7 or 8 seconds of travel time, 10 BSMs a second, 70 to 80 BSMs traveling down that block. Well, I can tell you from a system perspective, I don't need all that information to come up with a travel time for the block. So we are using 2 or 3 BSMs per vehicle, and the rest can go over the air and remain over the air for everyone else to use, but we'll only send those 2 back to the traffic management center. A tremendous reduction. For optimizing intersection control, we might need to know the BSMs from vehicles at the end of the queue, but does it help us tremendously if we have the BSM from every vehicle in the queue? Probably not. So we looked at our data collection for the project performance measurement needs. And we decided what we needed was information around the incidents themselves, the alerts that we're providing to the driver. We're doing that by aggregating, as Mohamad mentioned, time before and time after the warning, so that we can do a before-after analysis to understand what the vehicle was doing, when we provided the alert to the driver, and assess whether the driver responded to that alert or ignored it or took some corrective action. This sheet gives you some idea of the pure numbers we're looking at, and in some of the scenarios we're looking at the project possibly capturing over 200 terabytes of data. I don't want to be dealing with 200 terabytes of data. Hopefully these approaches will let us tailor and create smaller subsets that are useful. And then we're going to have to obfuscate that data because there's enough information in there to tell time and place. And if you start merging this data with other databases, you can look at potentially violating privacy. So we're scrubbing the data before we publish it. And then in the other area we're looking at extending is operations data, because many of the projects were of a size that they could send a vehicle out and test RSUs on a weekly basis that they're communicating. We don't have that luxury with 350 devices. So we're pushing that agenda too. My time is up. So we had a lot of lessons learned that we've applied to the project. You've heard some about those. The security issues, we've had to make our system secure to connect to the security system. That's how the big umbrella I put it under. And we've had to make additions like a hardware security module at the TMC to sign messages. So we've been learning as we've gone along. Stay connected. If you want to ask me any other questions afterwards, please do. We're trying to help the community and not just finish our projects.
Maybe we're going to have time for a few questions. If I can invite the panelists, Mohamad, Dave, and Jonathan. Any question on the audience, please? Yes,
A question for Mohamad. In your installation for the OBU, did it violate any of the vehicle guarantee warranties?
We're using OBD2, so
I'm sorry?
we're using OBD2, so I'm not violating. However, our requirement with our installation contracts that he would cover by his insurance any issues that can be resulted from any connection to the campus. We have made several tests already. As I mentioned, we have over 78 vehicles. We've already tested our connections. Some of our stuff, it was first time, but we don't envision to have any issue with the manufacturers. Also, we are in touch with the manufacturers on those issues. On those, this is our intention, this is our plans. Some of the information they don't really share. Some of the manufacturers, they don't want to share their configuration. They have their own OEM CV applications. That's fine. We have different ways to deal with that. So, like, elaborate more on the
We're actually taking two different approaches to dealing with getting the supplemental data. One is the addition of a, we call it a gateway bus, a gateway device that can listen to other messages on the bus. And the second approach is to only collect the speed information so that we can provide that to the GNS chip, which also incorporates the dead reckoning. So we're taking the two approaches to see what works best for us.
We have time for one more question. Dennis?
Sure, a question for Jonathan. Jonathan, one of your slides mentioned Wyoming numbers on truck accidents in 2017 and lower numbers. Was that because of what you did or was it just coincidence?
So to be honest, I don't know the answer to that question because I didn't generate that slide, but I just know from the fact that a number of the accidents that they have, and one of the things that was actually missing on there was the number of deaths. So sometimes it's not always the number of vehicles that are involved, it's the actual casualties. So that's always gone up each year, which was not displayed on that slide. If you want, I can find out more information on that. You can send me an email and I can give more details on the statistics and reference to that.
I think, Jonathan, that number was partial. 2017 is just partial. So it may not be fully a number. But it was increasing every year. When you said 2007 in the penalty, it's partial. It's not going to be a full body of data.
Yep, you're probably right on that.
Okay, a last question. You had a question?
Someone had, so.
Yeah.
So I have one last question. Okay.
Just looking towards the future, like, is there any thought to being able to use smartphones as like the transponder on the vehicle or on the pedestrians to carry out
very challenging question. Many vendor manufacturers, service providers, who really creating smartphones for us are working on this. However, the first challenge is the location identification. They have in the smartphone right now a GNSS service that can provide that accuracy to have the proper. The smartphone is being used with our pilot to serve the entire pedestrian, and basically just to provide the pedestrian in the crosswalk information, safety information that he needs to complete this crossing and to avoid that there's the walk indication is not there. I believe the work is there. It's more of, again, it's a technical challenge for the industry. It will head that way in the future. And they are using both actually today. They're using the 4G and they're using also the DSRC, which has been demonstrated for us just 2 weeks ago in the ITS World Congress. So it is possible, but it's in the making and it's going to take a couple of years. It's premature.
And thank you, we're out of time. Please join me to thank our panelists.
So I would like to thank the panel for a great discussion of what's happening in New York City in terms of connected vehicle pilot. I've done many of these deployments as an applied researcher, and really the detailing is in the details. And it's such a big project, really, it's really exciting to see how many challenges they're facing and solving every day, and we're really happy to be part of that project and learning us and our students how to deploy a very large-scale project.